All right, good morning, everybody. Thanks for coming to our talk about tuning packet and interrupt latency for 5G. This talk was originally planned for 40 minutes, so we're really going to compress it by talking fast. No, actually, we're not going to do that, but we've got some background material. Certainly, we'll post that in the slides, and we'll point you to some reference materials as well. So, we want to just give a quick overview, tell you a little bit about ourselves as well. My name is Ian Jolliffe. I'm an architect at Wind River and work on our Titanium Cloud family of products. And this is Chris.
I'm Chris Friesen, and I'm a senior member of the technical staff at Wind River. I contribute as well in Titanium Cloud, mostly in Nova.
All right, so Wind River's an interesting company. It's got software in 2 billion devices on planet Earth, but also on Mars. So we have software that actually runs on the Mars rover, or ran on the Mars rover. Little interesting fact. Our major area of interest is software-defined infrastructure. We have developed a cloud-based product that's focused on RAN deployments and edge deployments. And it's a really interesting area, certainly in 4G networks, but we really believe that in 5G it's going to be even more exciting. And some of the density improvements in subscribers, like millions of subscribers per radio zone, extremely low latency, and even pushing more compute out to the edge, I think is really going to drive a huge transformation in what we're able to do in networks and in a number of new and exciting applications. So really we think that a 5G network evolution, and the standards have made it really nice so that you can go from 4G to 5G, but this is really going to be a great enabler for the Internet of Things and connecting more and more devices at lower and lower cost. It's really going to be transformational. So some of the use cases we've seen are putting clouds at the base or at a wind farm. So a wind farm has lots of computation going on, optimizing the direction of the nacelles, and connecting up to all those devices via wireless is also going to make it much, much easier to monitor and migrate these things. In terms of the industrial internet, certainly in factory automation, continuous and discrete manufacturing processes, the ability to hook a sensor up to a continuous refinery process and run a small cell gateway to be able to connect up to sensors that cost pennies, have very long battery life of 10 years. It's really going to allow new ways to automate, new ways to investigate and optimize industrial control. Everybody's heard a lot about the autonomous vehicle. Autonomous vehicles are said to generate upwards of 1 terabyte of data a day. So that's going to be really interesting. How do you backhaul that? Is that really possible? Does that even make sense? How do you want to use that data at the edge of the network? So again, very interesting. And then lastly, telemedicine. It's been talked about for 20 or 30 years, but maybe there's going to be some really interesting opportunities to put small clouds and do analytics for medical imaging right in hospitals versus in a public cloud. So we're going to quickly touch on some really low-level technical ways that we can address the low latency and really drive extremely high performance and low latency to the edge of the network. We're going to talk about some optimizations for networking, how to configure memory and CPU within your cloud, and then also what are the best ways to configure your host OS as well as the OS and the guest to really come together for a full end-to-end solution. There's some great techniques in Nova and other ways within Neutron to actually configure all these things, and we're going to quickly go over those. So I'll turn it over to Chris to walk you through that.
Thanks, Ian. So the first thing that I want to talk about is simply just the networking itself, how you get the packets up into your virtual machine. But in the default case, you would have your standard interrupt-based kernel mode driver, both in the host and in the guest. You can gain significant performance by moving to a pole mode driver in both the host and the guest. One of these would be something like Intel's DPDK stack. This will gain you a noticeable performance improvement and a noticeable latency improvement. The downside is that you need to dedicate your cores on both the host and the guest to packet processing. If you're chasing the absolute lowest latency possible, you may want to keep the DPDK stack, the Pulmo drivers in the guest, and move to SRIOV or PCI pass-through on the host. This has the downside that it moves all of your routing to a top-of-rack switch. It also means that you can no longer live migrate your instances. The next thing I want to talk about is the memory considerations. As a basic starting point, I would recommend that you're using pre-allocated huge pages for the memory for backing your virtual machine. In our experiments, we found that the 2 meg page size is the sweet spot. Moving to 1 gig pages generally doesn't buy you a lot. The other thing that's important to consider is the cost of messaging between NUMA zones. So I would recommend that you enable the NUMA topology filter in the Nova scheduler. This will co-locate the guest, any PCI devices that it's using, and eventually we'll want to try and co-locate it with the vswitch process as well to try and minimize the amount of transactions that have to cross the NUMA zones. There's also some interactions with the L1, L2 cache that actually ties into the CPU considerations, which is what we're going to take a look at next. So as a basic starting point, I would recommend that you are using dedicated CPUs. This will ensure that each guest vCPU is mapped one-to-one with the host pCPU. This will reduce the amount of overhead that the host scheduler has to do. It will also minimize the amount of disruption for your guest processes. Normally, we would recommend that you use the isolate CPU thread policy. This will ensure that if you have hyperthreading enabled on your host, it will only use one of the hyperthread siblings to run guest vCPUs. In some cases, you may be able to gain performance by using the preferred or require CPU thread policy, where you will actually use both of the hyperthread siblings. This can gain you performance, but under very specific circumstances, it may also mean that your power consumption goes up. So I would recommend that you actually test this out, see whether it makes sense in your specific environment for your specific application. In some circumstances, you may want to enable the CPU real-time option. This will ensure that your vCPU threads on the host run at an elevated priority and scheduler policy. If you do this, you will also need to set the CPU real-time mask, which defines which vCPUs should not be real-time. The way it's set up right now is a little bit confusing, so I'm in the process of submitting a change upstream, which will make this a little bit more clear. So keep an eye out for that. The other thing that you may want to do if you need low latency on all of your vCPUs, there's something called the isolate emulator threads policy. What this will do is it will allocate for each virtual machine that enables this, it will allocate a separate pCPU on the host in order to run your emulator and I/O threads.
Chris and I actually did a talk back in Boston about some of these topics in a lot more detail, so look us up from Boston and you'll get some more info on that as well.
So the next thing we want to talk about is the host configuration. The most important thing to do on the host is to dedicate certain CPUs for your host overhead and push all of the host work onto those CPUs. That way you can free up all of the other host CPUs to run your guest work. The other thing that you need to worry about is SMIs. Depending on how your BIOS is configured or how the BIOS is written, SMIs on the host, if they interrupt the CPUs that are running your guest work, can cause latency in your guest packet processing. On the host, you may wish to use the preemptible kernel. This will give lower latency if your task isolation is not perfect. Then finally, there are a bunch of other possible tweaks. Look at the network latency settings in TuneD. They'll give you an idea of all of the things that can be done. And finally, on the guest OS, this is also important because the overall latency is the sum of your host latency and the guest latency. So in short, essentially all of the same things that you can configure on the host also should be configured in the guest to minimize your overall latency.
All right, so thanks, Chris. That was a great overview, and I think packet and interrupt latency are going to be absolutely critical to 5G, and I think we definitely see the way forward with OpenStack to be able to enable those new exciting use cases. So thanks very much for your attention, and I think there's maybe 1 minute left, so probably take a question. Thanks, folks. Yeah, sure.
So with OVS and sort of PMD thread limitations, have you had much success in increasing the efficiency of OVS by increasing PMD thread allocation and adding in like multiple RX queues?
Yes, certainly with OVS along with DPDK, that's a really strong solution. And DPDK now supports multi-queues as well, so that's absolutely a really good way to go. Yeah. I think we're out of time, so thanks, guys. Appreciate it.